Down at the runway threshold, an aircraft fights violently through turbulent crosswinds just to keep its gear aligned with the pavement. Yet a few miles straight up, that same aircraft might ride a perfectly smooth 100-knot tailwind. We define wind strictly as the horizontal flow of air across the Earth's surface. It is a mass of fluid put into motion entirely by differences in atmospheric pressure. But this creates an operational paradox. The wind speed and direction reported by the control tower at the surface is physically distinct from the air current flowing just 5,000 feet above it. Ascend even higher, to the upper limits of the troposphere, and the atmosphere reorganizes again. These elongated streaks of cirrus clouds reveal massive, high-velocity currents roaring at the edge of space. These drastic altitude-based changes are not isolated weather anomalies. The atmosphere operates as a highly deterministic system of fluid dynamics. Accurately predicting the air's movement requires treating wind velocity as the product of a specific mathematical balance. Every gust, draft, and current is the exact resultant vector of three specific variables: the pressure gradient force, the Coriolis effect, and surface friction. Mastering these mechanics allows a pilot to calculate the unseen forces of the atmosphere before they affect the flight. To isolate the primary driver of atmospheric movement, we must first picture a hypothetical, completely stationary Earth. Here, the pressure gradient force, or PGF, dictates the action. PGF naturally accelerates a parcel of air in a direct, perpendicular line outward from a high-pressure zone and into a low-pressure zone. If this inward pull were the only force at work, global high and low pressure centers would equalize almost instantly, and the wind would cease to exist. But the Earth is constantly rotating. The physical surface of the planet is continuously moving beneath the moving air mass. This rotation generates the Coriolis effect. As air moves, the surface lags, causing its path to physically deflect to the right. Crucially, this deflection strength relies entirely on the air's velocity. Faster air creates a proportionately stronger rightward pull. The initial forward acceleration toward the low pressure constantly fights against this intensifying rightward curve. Because of the planet's rotation, a parcel of air is entirely incapable of flowing in a straight line from high to low pressure. What happens to that parcel of air when the rightward pull of the Coriolis effect finally equals the inward acceleration of the pressure gradient force? The two forces enter a state of balanced flow, officially known as the geostrophic wind. Zooming out to the macro level, this balance creates a strict pattern. Air flows predictably clockwise around a high and counterclockwise around a low. This is a meteorological weather map showing large-scale pressure systems. Because geostrophic wind flows parallel to these plotted isobars, forecasters can accurately calculate wind speed based entirely on how closely packed the lines are drawn. We can translate this theoretical atmospheric physics into a practical, actionable rule for pilots in the air. Formulated by a Dutch meteorologist, Buys-Ballott's law states that in the northern hemisphere, if you put your back to the wind, the low-pressure center will always be on your left. This means you can read your aircraft's crosswind drift to orient yourself. If you are experiencing left drift, the wind is hitting the right side of the fuselage. Your back is to the right, meaning the low is behind you, and you are flying toward higher pressure. Conversely, if the aircraft requires correction for right drift, the wind is blowing from the left. You are actively flying toward a low-pressure system. Unknowingly flying toward lower pressure introduces significant physical hazards. Your altimeter will overread your actual altitude, and you will likely encounter deteriorating weather, low clouds, and poor visibility. Geostrophic balance turns simple aircraft drift into a diagnostic tool for mapping macroscopic pressure systems miles ahead of your flight path. But this model reveals a contradiction. If planetary physics dictate that wind flows parallel to isobars, why do control towers consistently report runway winds cutting directly across them toward low pressure? The answer lies in the friction layer, a turbulent boundary extending from the Earth's surface up to approximately 2,000 feet above ground level. Down here, rough terrain, urban buildings, and geographical features physically drag against the air mass, significantly bleeding off its velocity. Recall the critical rule of the Coriolis force. Its deflecting power relies entirely on the speed of the air. As ground friction slows the wind, the Coriolis force mathematically weakens. This loss of rotation breaks the balanced flow. The unopposed pressure gradient force overpowers the rightward turn, pulling the wind inward across the isobars toward the low. This specific counterclockwise shift in surface wind direction is defined as a backing wind. This effect changes with the sun. During the day, solar heating creates vertical mixing that pulls the faster parallel gradient winds down closer to the surface. This causes daytime winds to speed up and veer clockwise. At night, that vertical mixing stops. The surface air separates from the upper flow, slows down against the ground, and the diminished Coriolis effect causes the wind to significantly slacken and back. Those unpredictable runway crosswinds are not anomalies. They are the direct, measurable result of the Earth's physical surface breaking the delicate vector balance between pressure and rotation. Leaving the friction layer behind, we ascend into the high-level weather zone. We're now at the tropopause, the border separating troposphere from stratosphere. Rather than a continuous flat sheet, the tropopause features massive vertical steps that separate global circulation cells. At these steps, freezing polar air masses sit directly adjacent to warmer mid-latitude air, creating a severe thermal clash. Cold air compresses its pressure levels, while warm air expands them upward. This extreme horizontal pressure difference triggers an intense air rush. The extreme velocity causes the Coriolis effect to violently turn it right, creating a massive geostrophic vector. This creates the jet stream, a highly concentrated tube of westerly wind that frequently exceeds 100 knots. These sheer speeds pose a severe operational threat to commercial aviation, primarily generating invisible, violent, clear air turbulence along the sharp edges of the stream. While surface friction destroys balanced flow at the ground level, extreme thermal boundaries hyper-accelerate that balance at the edge of space, turning basic wind into a structural hazard. The atmosphere operates as a unified physics engine, where every altitude layer is mechanically connected. At the surface, ground friction dampens rotation, allowing pressure to pull the wind inward. In the mid-levels, undisturbed forces balance perfectly, creating smooth, geostrophic highways flowing parallel to the isobars. And at the tropopause, sharp thermal boundaries supercharge these forces into narrow, turbulent jet streams. This physical stack dictates the strict aviation communication standards pilots rely on daily. We begin with local airport control. Because a pilot's magnetic compass and their visual alignment with the physical runway are critical during the friction-heavy takeoff and landing phases, surface winds are always spoken in degrees magnetic. Forecasts at altitude operate differently. Because jet streams and gradient winds dictate long-range global routing over a map, winds aloft are strictly written in degrees true. This equation provides the technical framework for navigating the invisible fluid dynamics of the sky. Wind is a predictable mathematical inevitability.